Hi, I'm Brian Walton and I have a video for you to illustrate how to do a transformation of a function by centering, scaling, and maybe flipping your model. The strategy that I'm going to illustrate applies to functions that have natural length scales horizontally and vertically and are in their native sense positioned relative to the origin. So here I have a number of different functions for which this applies. For example, the parabola. We can look at the parabola, and the vertex of the parabola takes place at the origin, and it has natural length scales horizontally and vertically, so that my natural length scale in the x position is 1 and the natural length scale in the y direction is 1, because if I go over 1, the parabola goes up 1 and from the vertex at the origin. Next, we take our attention to the exponential doubling function. Again, we think about the origin as our starting position, and the cool thing about the exponential doubling function is that as I go from the origin, its natural height is 1. If I go over 1, its next height is 2. If I go over 1 more, the height is 4. It keeps doubling every time I go over. And so this has a natural vertical scale, it's meant to draw, has a natural vertical scale of 1, and the natural horizontal scale has to do with this doubling. I have to go over a natural length scale of 1 in order to get that doubling. And every time I move over that length scale of 1, the function doubles again. Next, I want to pay attention to the reciprocal function, where I take y equals 1 over x, and this is relative to the origin in a special sense that this function has a horizontal asymptote of y equals 0 and a vertical asymptote at x equals 0. So the origin is the crossing of the two intercepts. There's a natural length scale based on this graph as well, going through 1, 1, so that I have a natural vertical length scale of 1 and a natural horizontal length scale of 1 as well. Notice that that's actually the same length scales as the parabola, and that's because both of these are power functions. And by that I mean that this power function, because I can write 1 over x as x to the minus 1. For my last example of a function that has a natural scale, I want to look at the cosine function. I could have used the sine function, but I'm choosing the cosine function just to emphasize that the graph doesn't have to go through the origin. But again, if I look at the origin, this is special because it corresponds to where my function goes through its peak. And if I want to know a length scale, I want to see where that peak happens again. So here it is at 2 pi. So this gives me a horizontal length scale of 2 pi and a vertical length scale corresponding to the amplitude of 1. Now I include this slide in my video to summarize what I'm about to do. I'm not really going to spend a lot of time on this. You can pause it and read it. But the basic idea is I have a function at y equals f of x, and that original function has natural length scales that I'm going to call little l x and little l y. It goes through the origin, and what we're going to do in each problem, we're going to see where the center point goes, and in this I'm calling it generically AB, and I also find new length scales in my transformed graph. And what we're going to do in every example is we're going to define new coordinates where we center by subtracting our center coordinates, and then we're going to rescale by dividing by our new length scales and multiply by our original length scales. And this is going to be used in our function. Instead of y equals f of x, we're going to transform it, and then we'll solve for that new y variable that in this example I'm calling the transformed coordinate v. That's what we're going to do in every example. And to see how that works, just keep watching. For our first example, let's look at a shifted and stretched parabola. The basic function is y equals x squared, so we are going to look at the elementary graph y equals x squared. We just want to remind ourselves that the vertex is at the origin, and we have natural length scales corresponding to the point 1, 1. The natural length scale of x is 1, the natural length scale of y is 1. Now what we need to do is we need to find the corresponding center point, so our vertex, and we need to find a natural length scales for x and y. So our vertex in this example is at the point 2, -3, and if we look for another point on the graph, I see this one, and so we're going to pick our length scales to match that. So we see how far our length scale for x is, just to keep the variable different, emphasize its new coordinates. We figure out how far we've gone, and so the change in x here, based on going from 2 to 5, the natural length scale is 3. Just remember that's a change in our x coordinate. And the natural length scale for y is 2. That's the change in our y coordinate. Now that we know our length scales, we can define our variables by centering and rescaling. So my x variable is my coordinate minus my center point divided by the length scale times the length scale of our original, and just remember that's 1, so I don't need to do anything else. And my y coordinate is similarly my y variable minus my coordinate of the center point divided by the length scale. So what we're going to do is we're going to take our formula y equals x squared, that's our function, and our transformed coordinates, we use what we just found, that we had v plus 3 over 2, that's y, equals x, so that's u minus 2 over 3 squared. That is the equation of my transformed parabola. And all I need to do is solve for my variable, my y variable, v, so we'll multiply by 2 and add -3. So 2 times u minus 2 over 3 squared minus 3. This is the equation of my new parabola. I usually want to write that in terms of my original variables x and y, and so in the language of x and y, my function is y equals 2 u minus 2 over 3 squared minus 3. Now if I thought about my original function as the squaring function, then the way that this function would be written is I've doubled the function value. Oh, I meant to say something else up there. That should have been x. It's the function of x minus 2 over 3. So this function is squaring this quantity, and then I double it and subtract 3. And that would be how I graph in the language of the function. And this is how I would put the formula, maybe in a calculator. For our next example, we're going to look at an exponential function. And one of the things I want to point out is in this example the exponential's decaying as opposed to growing. So we'll have to take that into account with a reflection. If I go and look at my original exponential function, and I've chosen here the exponential doubling function, the origin, which is where we always start, our length scales are going to be defined in the context of that. So I have a natural height length scale of 1. And when I think about the length scale in the x direction, again I want a length scale of 1. And that's defined because every time I move over 1, my function doubles. So it starts at a height of 1. As I go over 1, it's now at 2. If I go over another 1, it's 4. If I went over another 1, I'd be at 8. And so that's how I define my length scale. When I look at my transformed function, I need to find a origin and, a center point, and I need to identify my length scales. I could pick the origin as my center, but the problem is I don't really know exactly what point that is. So I want to look for some other points that maybe are a little more clear. As I look along the graph, notice 2 looks like a height 3, and x equals -1, I've got a height of 6. So I've got these natural heights, and at -4 I'm all the way up at 12. So I could pick my origin maybe to start here at 2, and I'm doubling every time I go back 3. And so this is where the reflection comes in. Instead of going forward, my length scale horizontally is actually going to be backwards. It's -3 to take into account the reflection. And so I've got an origin, and I also need my vertical length scale. And so my vertical length scale for this problem happens to also be 3, but that's because at my center point the height of the graph is at 3. To get my transformation, what I'm going to do is I'm going to be, and I probably should have said this in the previous graph, I'm thinking of my axes so that I can keep the difference between my original graph and my new graph. I'm temporarily renaming them, and I'm going to call my transformation, my x coordinates are my centered u, so u minus 2 because that's where I called my center point, and divide it by my length scale, -3, and my y coordinate is my v minus the center point 0 divided by its length scale, also 3. Now, we haven't been doing anything with these other length scales because for both of our examples so far, those were both 1. So what we'll do is we'll take our function, y equals 2 to the x. I need to draw, don't I? Y equals 2 to the x, and we're going to use our transformed variables. Y is equal to v over 3, and we'll replace x with our transformed coordinates u minus 2 over -3. I want to solve for my y variable v, so v is going to be 3 times our function 2 to our transformed x coordinates. We usually want to think of this in terms of our natural variables x and y, and so our transformed graph is 3 given by our vertical scale of 3 times our function 2 to the graph, 2 to the power x minus 2 to center it, divided by -3 to rescale it and to reflect it. And that is the equation of our graph. For our last example, I want to look at the cosine function and the sinusoidal graph. The cosine function, just to remind you some of the basic features, if we think about it, center point as the origin, the vertical scale is 1, but this is our first example where the horizontal scale, the natural length in the horizontal direction, is not 1. In fact, it's the gap from peak to peak, or the period, which is 2 pi. And so our horizontal scale for the cosine function is 2 pi. Now, as I look at my new graph, I look for where the peaks are, and so notice I have a peak at -5 and at 1, and a minimum at -2. I need to find the center line, because the origin, our center point, is going to be on that line. Now, I have several choices I could pick. I could pick my origin or my center point to be here at -5, 3, or I could pick it here at 1, 3. Doesn't matter, I could pick either one. I'll get a different formula for those two problems, but they'll be the same graph. It's kind of a cool thing. And in fact, I could also pick, if I include a vertical reflection, I could have picked -2, 3. And just to illustrate how a vertical reflection works, I'm actually going to pick this point -2, 3. So that's going to be my center point. And notice that this time, because of that choice, my vertical scale this time is upside down, and my vertical scale is going to be -2. My horizontal scale, I need to go all the way, I need to figure out how much that period is, and this time, peak to peak, my horizontal scale is this gap from -2 to 4, and so my scale is 6. Okay, so I have my center point, I have my two scales, and now we're ready to go. Okay, now the difference this time is when I create my x variable, I have to include that original scale of 2 pi coming from my period. Now we'll center our point, so we did u minus our coordinate -2, and our horizontal scale instead of 2 pi is 6. And our y coordinate, let's see, we had a center of 3, so it's v minus 3, and we had a vertical scale. The amplitude of this graph from the center line to the peak is 2. Oh, but it's we've reflected it, so I need to be -2. Okay, so let's simplify these out. Notice that I could simplify that 2 pi over 6 to be pi over 3, and u minus -2 is u plus 2. And let's rewrite this as v minus, I guess we didn't need to rewrite that, v minus 3 over -2. Our original graph, y equals cosine of x, in our transformed coordinates becomes v minus 3, include that vertical reflection, that's our y, equals the cosine, and we'll now replace x with its transformed value, pi u plus 2 divided by 3, or 2 pi over 6. That's the equation of our new graph. Of course, we want it solved for our v variable, so we're going to multiply by -2, keep our x coordinates as is, and we need to add 3 to solve for our v variable. In our transformed coordinates, u and v, we have the equation of our graph. And as for our previous examples, we really want this in terms of our natural variables y and x. So we change our variable v to y. We get y equals -2 cosine, and we'll change our u to x, so pi times x plus 2 divided by 3 plus our centerline height 3, which I want to emphasize this value 3 corresponds to the height of 3, or the y value of our center line given by our center point, -2, 3. And this constant -2, just a reminder, corresponds to our amplitude, which in this case is upside down because of where we chose our center point. Okay, well, hopefully this is a good help for you to be able to transform functions by finding out where the center point moves and how this length scales change. Good luck as you do problems.